nobody's using it. Okay, all right. So welcome to the final episode of the 2018 season of Supercomputing in Plain English. And today we have a bunch of different topics. And of course, we have all of our usual stuff that by now we've all learned to ignore. But we can always look it up if we need it. Blah, 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 blah. And this is it. Yeah, this is the very last one. I wasn't kidding. It says so, so it must be true. Okay. And thank you to everyone who helped. I'm happy to report that for the PERT 2018 conference we just found out last week that we have a paper published there. So that's very exciting. And it turns out we won't have to hardly do any edits. In fact, that paper, I'm delighted to say, got the best ratings in the reviews of any paper I've ever done. So I feel very happy about that. I don't know if I earned it, but I'm happy about it anyway. Okay, all right. So we're going to talk about scientific computing pipelines, scientific libraries. These are really sort of the three major topics here: the scientific libraries, IO libraries, and visualization. And I'll just ramble on until either I run out of slides or we run out of time. Okay. So a friend kind of gave me this. Julie Mullen at MIT Lincoln Lab came up with this. So if you think about what it is we're trying to do compared to how we do it. At the far end, we have reality, okay? Reality, things are happening in the real world. Then there's the physics description of what's happening in the real world. And then we represent that physics with math, typically with some kind of, let's call it calculus, differential equation or what have you. But it's a continuous representation, not discrete. But then we have to approximate that. It turns out that almost none of the equations we're trying to solve can be solved in closed form. Almost all of them have to be discretized and represented numerically. We then have to come up with an algorithm. And so I'm going to go all computer science on you on this one. So in computer science, we have a very specific meaning to the word algorithm that nobody else in the world uses because everybody else has a fuzzy idea of what that word means. So an algorithm to us is a description of how to solve a problem, not the solution to the problem. That is, the algorithm is not the same thing as the implementation. A lot of times you'll hear folks from the consumer side of research computing, people who are doing research computing as opposed to providing it, they will use the word algorithm to mean code. And computer scientist in me objects to that a little bit. We think of the algorithm as the pseudocode that describes how you solve a problem. But anyway, then there's the implementation, which is the program. Then you have to have that implementation work on a particular kind of computer. So that's the port. Then you run it and you get the result. Then you have to do some analysis. What does that result mean? And you have to verify that your code is actually working. And I'm always getting confused between verification and validation. One of them means the code works, and the other means the code represents the real world reasonably well. And I can never remember which one is which. And I can convince myself that either arrangement is the right one. So, but this leads to a lovely set of principles that if you reorder them, they turn out to be quack. But know the physics, control the software, understand the numerics, achieve the expected behavior, and question behavior that is not expected. And the issue here is it's entirely too easy to believe that the code knows what it's doing. The reality is the code doesn't know what it's doing. It's a little bit of story time for you. Many years ago, I was working with a good friend who's a chemical engineering faculty member here at OU. And we wrote some code together. And the code was, for the particular case that we were running, the code was doing things that I guess the technical term is aphysical. It was doing things that in the real world are literally impossible. And we were trying to figure out what it was. Was the math wrong? Was the code buggy? Was the physics wrong? We were trying to figure that out. And what we discovered was, the real problem was that the code assumed that there was a reasonable, it was a bunch of tubes connected together and the physics of the tubes. Well, the code assumed that the tubes were tubes and not disks. And it turned out that we were trying to move this fluid down a very large disk that was very, very short. And that was outside the realm of what the math could handle properly. The hidden secret assumption in our approach to this was that the ratio of the diameter to the length was not really, really close to infinity. So in other words, that the thing was not infinitely short. So once we realized that that was the problem, we changed some of our inputs and we got a reasonable result. But you really don't want to trust the code, because the code is always wrong. And the reason the code is always wrong, aside from the usual every code has bugs. By the way, how do we know that every code has bugs? Years of painful experience is half the answer. But the other answer is, even if the code doesn't have bugs, the code has to run on top of the operating system. And the operating system, I promise, has bugs. And by the way, you had to compile the code with a compiler, and the compiler has bugs. So even if the code is perfect, which it ain't, but even if it were perfect, still, the code is full of bugs. Anyway, so you want to be very, very skeptical of the results you get and see whether the results you get really do make sense in the real world. Okay, so scientific libraries. We remember many, many, many weeks ago, we looked at this example of matrix-matrix multiply. I think it was in week two. We started looking at this. Matrix vector multiply and solving for a system of equations. So it turns out that solving systems of equations like this, linear systems of equations, where you have a matrix of coefficients, you have a vector of unknowns, and here's a vector of knowns on the other side of the equal sign. It turns out that the way that you solve that in practice involves a lot of matrix-matrix multiply. So the underlying performance for that is built on top of something simple like matrix-matrix multiply. Okay? But this is a very common problem. And by the way, if it's a nonlinear system of equations, one of the ways, not by any means the only way, but one of the ways that you can solve a nonlinear system of equations is by repeatedly solving a system of linear equations, or a set of systems of linear equations. So it turns out that this method is useful in a lot of different contexts. Okay? Now, here's the thing. You can always write your own solver. You can always write your own matrix-matrix multiply. And we did that in week 2. We saw a lovely matrix-matrix multiply routine. It's very easy to write, right? It took me 5 minutes. It's no big deal. And then another 5 minutes to write it in the other language. But it's not the most, it's not the fastest version. It's going to have some insufficiencies, let's say. On the other hand, there are clever people who are paid full time to write those kinds of codes. Therefore, they write those codes so much better than we do. And if they're going to write those codes so much better than we do, and by the way, some of them provide the code they write to do these common tasks for free. So we can just download these scientific libraries. And I'll reiterate that in the context of computing, library means collection of routines. We can download these scientific libraries, compile them if necessary on the platform that we're going to be using to do our runs, and then use them in our runs. And we should do that because those people are much smarter than us about this stuff. We are smarter than them about our application, but they're smarter than us about whatever the particular library is supposed to be doing. Right? They know a lot more about that than we do. They've devoted their career. In fact, some years ago at our annual symposium in September, one of our speakers, in fact, I think he was a keynote speaker, was the guy who created a set of libraries for random numbers. He is one of the world's foremost experts on generating random numbers. And he's also, shockingly, a very interesting and engaging speaker, which is not something you would predict. But a wonderful guy, Michael Muskeni. We were very happy to have him come give a talk. Anyway, so very smart people know a lot about this stuff, way more than we ever would or would want to. So let's use what they created because it's there, they know what they're doing, and it means we don't have to do so much work. So again, very common problem people like to solve, solving systems of linear equations. Matrix of coefficients, vector of unknowns, vector of knowns. Very straightforward, solve for x. Good old stuff. All right, well, when I was a wee lad, there was, and there still is today, a wonderful magazine called Highlights for Children. Yes, question in TV land.
One of our participants want to know, how do we know which libraries to trust?
How do we know which libraries to trust? I'm going to point you at some. Beyond that, a good rule of thumb is ask others in the community, because as a general rule, there will be a consensus, and the bad ones, they can tell you the horror stories about, and they will not be shy about sharing those horror stories. And the good ones, they will gushingly praise. So very quickly, by asking your colleagues in the same field, you will find out which things are in common use, okay? All right, so in younger days, we had this magazine that my parents actually got us a subscription to, but otherwise we would find at the dentist's office because we were, little kids, and so we went to the little kid dentist. Highlights for Children, it was called. It's still out there, they're still making it. And it, it had little activities and coloring, I don't know what all, but one of the regular features of Highlights for Children was this wonderful thing called GOOFUS and Gallant, okay? And so I had occasion a few years ago when I was working through this talk, I thought GOOFUS and Gallant would be a really good way to capture the do's and don'ts concept, things to do and things to don't, right? When doing these kinds of calculations. And it turns out that GOOFUS and Gallant was actually kind of edgy in a way that I hadn't anticipated. So here's a good one. GOOFUS runs with his scissors pointing up, whereas Gallant walks with his scissors pointing down. And if you read enough GOOFUS and Gallant, you kind of start hating Gallant because he's such a goody two-shoes, right? So GOOFUS says, here, sew this button on. And Gallant says, will you please sew on this button, right? He's so sweet and nice and polite and thoughtful, and you just want to slug him. And what I don't show you in these slides, but I actually found on the web was there's one where GOOFUS actually tells one of his siblings that he hates them. It's just really mean. GOOFUS is just awful, but he's really entertaining. All right, so anyway, so the don'ts. Number one thing, if you're trying to solve a system of linear equations, don't invert the matrix. This is sort of what we learn in math class, and mathematically, there's nothing wrong with it. But there's two problems with it in real life why you don't want to do this. Never invert a matrix in real life unless you absolutely have to. There are two reasons for that. One is it takes a lot longer. I think it takes 3 times as long, something along those lines, than to do a direct solve. And the second reason is it introduces a lot more numerical error. You're much more likely to get a bad answer if you invert the matrix. Instead, you should solve directly. And then don't write your own solver. If you're going to solve a system of linear equations, bloody well use the ones that other people have devoted their careers to writing. Okay. All right, oh, here we go. GOOFUS and Gallant. GOOFUS bosses his friends. Gallant asks, what do you want to do next? GOOFUS takes the apple. Gallant shares his orange. Okay, so are you starting to feel like a high degree of antipathy toward Gallant? I certainly am. Oh, look at this. GOOFUS leaves his books spread all over the floor. Gallant picks up his papers when he's finished. Like, I get what the problems with GOOFUS are, but Gallant really rubs me the wrong way. Anyway, all right, so things to do. Use these standard portable solver libraries. And one of the great advantages of that is then you can keep using the same code without having to update it when you get to a new kind of supercomputer, because they inevitably have ported that code, those libraries, to that other platform or a new platform. Use a version that's tuned for the platform you're on if possible, okay, if they have one. And use the information that you have about what you're trying to do to pick a better approach to doing it. It turns out these solver libraries, among others, oftentimes will handle special, let's say common special cases in a very graceful way to do better. So here's some things that happen a lot. So it's quite common to run into a matrix that is symmetric. So for any I and j, aij is the same as aji mathematically. So you don't have to like go looking through the matrix. You know that's going to be true before you get started. if you can use a routine that solves symmetric systems, typically it takes much less time. Okay. May also consume less memory. Positive definite, I'm not going to try and explain that really, but it means this thing, so don't worry about it. But if you know that your matrix is positive definite, if your matrix is banded, so 0 except on a bunch of specific diagonals, you can do it much, much, much faster. Tridiagonal is a special case of banded. But more generally, if you know your matrix is sparse, and by sparse, I mean the overwhelming majority of matrix entries are 0. Because multiplying something by 0 gives you 0, and adding 0 to something doesn't change the value of that something. Therefore, you never need to multiply by 0, and you never need to add 0. As a result, you can solve a sparse system of equations using a lot fewer calculations than you would need to do the equivalent, I don't want to say the equivalent dense matrix, because the matrix is sparse, but if you use the dense matrix approach to the sparse matrix problem, it would take a lot more calculations. Okay. Here's a picture. Now, this is from the same story as I told before about the things that were very short and very wide. This was the same thing. And so this is, well, I kind of left out. I want to tell this story because it's immediately relevant to what we're talking about here. So it was a sparse matrix, but the solver that we had at hand was a dense solver. And so we tried plugging the sparse matrix into the dense solver. And it would solve the sparse matrix sometimes for some instances of the problem, but not for others. It would fail. It would fail because it was discovering that the matrix had repeated values in it that shouldn't have been in there multiple times. So we went back to the math. I asked my colleague, so do any of these coefficients, non-zeros in here, are they the same as something else? And he said, oh, yeah. This thing here and this thing here are really the same. I said, well, then we don't really need to have it twice. Can we redo the equations to take into account that these two things are always going to be the same? He said, sure, let's do that. So we redid the thing, and it turned out it took it from a supercomputing problem to a laptop problem. It eliminated so much work, and the problem became trivial to solve. So one of the things that you should always make sure you do, no matter what you're doing, is make sure that you've done the math in the best way, even before you worry about the computing, because it's too easy to do the math in an inefficient or ineffective way, a way that makes sense to us mathematically, but doesn't translate well to computing. Okay, so there are a lot of good linear algebra libraries. So this maybe partially addresses the question from the person out in TV land. This is by no means an exhaustive list, but if you have these in your back pocket, you probably have much of what you need in order to be able to at least be able to do some linear algebra. And the first one that a lot of other packages are built on top of is called the BLAS. Now, that doesn't mean that you're feeling kind of not very enthusiastic about stuff. It's the basic linear algebra subprograms. It's a library of low-level routines, and they actually have 3 levels. And I hate this. I'm not a fan of naming things with numbers. So, for example, if you've ever done statistics, you've encountered an error of type 1 and an error of type 2. And unless you do that stuff all the time, you, like me, don't have much luck remembering which kind of error is which. So I'm not a fan of this, but level 1 in BLAS is vector-vector operations, so dot product, for example. Level 2 is matrix vector operations, so multiplying a matrix by a vector is probably the most common one. And then level 3 is matrix-matrix operations. Again, the most common is matrix-matrix multiplying. Okay. These routines are somewhat useful on their own, but it turns out they're even more useful if you've got something else that's built on top of them, which you often do. So I'm mentioning here Layback, Layback, and Petsy, and I'll talk about them in a moment. All of them are built on top of the BLAS, and so are many, many other packages. Now, it turns out that there is a version of the BLAS, an implementation of the BLAS, that uses what we sometimes informally refer to as a bake-off to determine what's the most efficient way, time-efficient way, to do these calculations. And the way that this works is when you build this implementation called the automatically tuned linear algebra software, or ATLAS, what happens is it tries every way it can think of to do each and every one of these zillion subroutines. So it takes an awfully long time to build. But what it does is it builds them in all the different ways and then runs them to see which one of those ways is fastest. And whichever one is fastest when it's doing the build, that's what it decides is the right way to do that thing. And it usually has anywhere between a handful to maybe a dozen different ways to do a particular calculation. And there are, I don't know, maybe 100-ish routines. So you can tell it's a lot of work to get this thing to build. On the other hand, that all happens automatically, right? And it says, oh, we'll just do that. Okay? And the whole thing is free. You can trivially download it. It's not that hard to build. Several years ago, I don't know what it is with patent clerks, right? Einstein was a patent clerk when he wrote his famous paper in 1902 or whatever it was. That was either general or special relativity. I can never remember which is which. Doesn't matter. So another patent clerk, this time in Japan, in the 1990s, I guess, or early 2000s, he discovered a hobby. I actually read an interview with him just recently. He discovered a hobby of writing linear algebra software to be really fast. Now, for me, that doesn't sound like a hobby, but he was all into it. He really enjoyed it. And he had this brilliant idea that it was one of those ideas that until you heard it, you would never have come up with it on your own. And then when you heard it, you were like, why didn't I think of that? It was an actual smack yourself in the forehead kind of idea. And his idea was this. Instead of trying to optimize for cache when we're doing these calculations, let's optimize for the translation look-aside buffer, for that little tiny cache that holds page table entries for virtual memory, which we have to go through the rigmarole of using, but is not terribly useful if we're not actually using virtual memory in the sense of using swap disk, which is super slow. So we don't want to do that in high-performance computing. But let's optimize for that before we optimize for cache, and that'll get us better speed up. And he was so totally right. And when everybody heard this idea, they were like, that's brilliant. I wish I'd thought of that. Right? So he was so totally right that for at least one of the platforms, at least one of the CPU flavors he was trying to run on, he was getting 99% of the theoretical peak speed of that chip flavor, which is unheard of. What I've seen for things like Atlas is more like 70, 80%. And he was getting 99%. It's unreal. It's unreal. And on most chip families that he was working on, he was getting in excess of 90%. So it was just amazingly good. What's happened since then is some of the platform-specific pre-tuned libraries that you can buy, or sometimes they come for free, depending on the kind of hardware you're buying. They now actually adopted a lot of his ideas. And so they get the benefit of the work that he did, even though it's not necessarily him doing the implementation. So Intel has a library that includes the BLAS. The ones that have stars also have other stuff in them, but includes the BLAS. AMD has a similar thing. IBM, Oracle. There's one developed for CUDA on NVIDIA systems. All these libraries are highly tuned, often using his brilliant idea. Okay? So what we have today is that if you're doing dense matrix algebra, you can get awfully close to the theoretical peak speed of your machine. Whereas if you're doing some memory-bound calculation, like a finite difference calculation, you will not get anywhere close. You will be lucky to get a few tens of %. So here's a comparison just using Atlas, and then the go-to stuff, depending on who it's implemented with, is going to show even better performance. And you can see this is the reference implementation, which does not do anything clever to do the calculations. It just sort of does the direct brute force naive way. Here's Atlas doing so much better, right? Doing 2.5, almost 3 times as fast because it's more clever. And then you can go even beyond that to cleverer ways. Okay, now, Layback, the linear algebra package. This is very good primarily for dense matrix algebra and special cases of sparse, like banded and tridiagonal and that sort of thing. And it provides a decent set of routines for a lot of different cases. So single versus double precision, real versus complex numbers, a variety of different shapes. So you got diagonal, bidiagonal, tridiagonal, banded, triangular, blah, 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 like a whole bunch of them. And then the general dense matrix. And a lot of different properties, so orthogonal and positive. I already mentioned some of these, symmetric, and of course the general one. And all of these, there's almost no calculations in the Layback code. The Layback code is almost entirely calls to BLAS routines. So it's completely, and if you have a fast BLAS, you automatically have a fast Layback because almost all of the work is getting done in the BLAS routines. So here's just a little example of that. This is kind of the Fortran version. I don't know if I included a C version. I guess I didn't. Okay, but this is straightforward, right? You've got your 2-dimensional matrix of coefficients. You've got your array of knowns, which is called V. Your array of unknowns called X. I don't know why V for the knowns, but there it is. You need some extra. This is a little matrix to do some extra help. So you build the vector of knowns, the matrix of coefficients, and then you just call this routine. So this is single precision general solver. It's solving the system of linear equations. And it's all magic. And when it comes back, the knowns have been clobbered by the unknowns, and you're done. That's it. So if your problem can be expressed as a dense solve, it's super trivial. And you have to learn almost nothing. Isn't that great? Now, it turns out that there's a wonderful place you can go and get a lot of these things. And going back to the question from the person in TV land, much of what's at this website, netlib.org, much of the stuff there is the sort of thing that has excellent reputations, and you should download it and use it if it's relevant to what you need to do. Okay. Layback itself, by the way, is also an API. You can always create your own Layback implementation if you want. Okay. And so here's another thing. Things that are popular are good. Not because they're popular, but as a side effect of being popular. In particular, software that is popular is good because it's well tested. So consider, for example, the difference between Ethernet and InfiniBand. Ethernet is used by virtually every computer in the world. Everything from your phone, which uses the Wi-Fi, to the biggest supercomputers in the world. InfiniBand is only used by big supercomputers and other applications. That's not the only application for it, but that's sort of the key one that we're familiar with, and certainly not used by every computer in the world. This means, so let's say there are orders of magnitude more computers that have Ethernet than have InfiniBand. This is not a slam on InfiniBand, it's just the needs are different. But the result of that is that Ethernet can't help but be much more robust because it's been tested in just about every conceivable circumstance. So it can't help but be more robust, more resilient, less likely to crash, less likely to experience bugs, because it did experience them and people figured out how to fix that. Okay? It's by no means perfect, nothing is, but it can't help but be better tested. So a good rule of thumb is you should use things that are as vanilla and popular as possible because they're more likely to be well tested. Okay. All right, so I've more or less talked about this, right? We've kind of gotten into that. Now, Scale Layback is like Layback. It's not a complete Layback, but it's most of Layback except done in multi-server configuration. So you can take a very big matrix that's too big for your laptop and split it up among many, many servers and do really, really big problems. Of course, that means that there's lots and lots of communication over the network, So it's very sensitive to that. It's also, to be perfectly honest, and I've used it a little bit or helped other people use it is maybe a more accurate way to say it. It's much more confusing to use and takes a lot more experience to use well. You have to spend a certain amount of time, a lot more time learning how to use it than you do with Layback. But there's payoff on the back end of that. Now, Petsy, Portable Extensible Toolkit for Scientific Computation, is a solver package designed primarily around sparse matrices and doing sparse matrix problems that are really big, so you want to run them across multiple servers, for example, using MPI. And in fact, that's what Petsy is built on top of. There is a dense matrix package inside there, but it's not, it's single server, whereas the sparse matrix package is multi-server. And so Petsy can be a big win for doing sparse problems, especially very large sparse problems. And my experience, and I've used Petsy a bit, my experience is that Petsy is much more straightforward to use than Layback. The difficulty with Layback, to be perfectly honest, was that it was originally designed around Fortran 77, and Fortran 77 is a terrible, terrible programming language. Whereas Petsy was designed around C, and C is a much more usable programming language than Fortran. I love Fortran 90, for the record. Fortran 90, I think, is swell. Fortran 77 is brain poison. And Layback was designed around that. So, all right, so depending on what you're trying to do, you pick your solver package. That's going to, and then all of these, you notice, are built on top of the BLAS. So you make sure you have a good implementation of the BLAS. It's going to get you close to theoretical peak, and that will get you a wonderful outcome. Okay, let's go on to I/O. How am I doing on time, Debbie?
It is 1:02.
Okay, so I'm halfway home. All right. Okay, so I/O. There are two difficulties with I/O. One of them is, well, there are three, really. I sort of left one out. So one of them is you want the I/O to go fast. The classic joke about high-performance computing. High-performance computing is about converting a compute-bound problem to an I/O-bound problem. That is, taking a problem that takes a long time to do the number crunching, make the number crunching take much less time, then the thing that takes a long time is writing the output to disk. Okay? So performance is a big issue. But on the other hand, you don't want that when you write out a file on computer type A, that you can't read it on computer type B. And I have a story to tell about that. So many years ago, our very first year as Oscar, when we had just opened our doors, we inherited at the tail end of its life a very large machine that its total compute capacity, its total theoretical peak speed, was less than that of one CPU chip in our new supercomputer. So we clearly wanted to push that big blue thing out the window. And we were prepared to do that, except there was one grad student who had done their entire dissertation research on that big blue box. And the problem was that they had done all of their output in the native binary format of that particular kind of computer, which was not a common binary format. And the only machine we had on campus that could read that format was that machine. So that was Christmas break of 2001. This grad student had to finish by the end of Christmas break because in January they were supposed to get on a plane and go back to their country of origin. So they had a very loud clock ticking. And the only machine that could read their data so they could analyze what was in it was that big blue box. And so we had one systems person at the time, and his job, that entire Christmas break, it ruined Christmas for him, was to come in about every second or third day and nurse the big blue box back to health so that this person could finish their dissertation before they had to leave the country. And it was a bloody nightmare. So this drove home. I already kind of knew, but I knew it intellectually. This made it internal. This made it core to my identity that you write your data in a format that can be read on any kind of machine. The third issue that I didn't include on the bullet list there is you just don't want to use more disk space than you need, right? Disk is expensive, and you don't want to overconsume. So you want to keep things at a reasonable level, okay? All right, so far so good. And bear in mind, I/O is super duper slow compared to everything else we do in computing. All right, so here we've got a print statement in C or a printf statement, sorry, print statement in Fortran or a printf statement in C or whatever. And we want to output it in some human readable way, right? So here X is assigned 5, and then we output 5. Boom, done, right? Easy. Okay. But what if the value you want to output has lots and lots of digits? Now, if you output it in a human readable format, and by the way, we love human readable output because then we can just look at it, right? That's great. But if you output something like this, so what does this work out to be? 1, 2, I guess I go to 9, 10, 11, 12, 13. So that's 13 characters, which is really 14, right? Because you're either going to have a blank space or a carriage return after it, right? It's not just going to sit there. You're not going to start the next one here, right? So that's effectively 14 bytes spent on outputting this number, right? Well, that's quite a bit. Because remember, each one of the characters you output takes up an entire byte. And when you store that number in memory, that's either taking up 4 or 8 bytes in memory. That is, it's either single or double precision. Right? So it's not taking up nearly that many. It's not taking up 14 bytes in RAM. So outputting even more than you're using in RAM seems like a waste. I don't want to do that. So instead, I like to output it in the binary format it's being stored in, right? And that's going to be 4 or 8 bytes, much less than 13, which is really 14, right? Much less. So far, so good. So that's trivial to do in most programming languages. You can just output it as binary data. It's no big deal. But the problem we have when we output it as binary, now, there are 2 problems, right? One is you can't actually look at it anymore. And the other is now you can't necessarily read it on another machine of a different kind. Right? And that can be a really big problem, as we found out way back in Christmas of 2001. Okay, we don't like that. Now, the readability issue is actually not that big a deal because you can always write a program that reads it in and presents it in a readable format. So that's not the end of the world. And if it's big, if we're looking at megabytes or gigabytes or terabytes, you're not going to want to visually inspect all of that anyway, because after the first 3 or 4 screenfuls, it doesn't mean anything. Right? Okay. But the binary portability issue is a really, really big deal because if you are not producing something that can be read on another machine, then your data essentially ages out. And that's more and more of an issue nowadays because nowadays the research funding agencies, particularly the federal research funding agencies, are requiring us to have plans for how to make the data available to third parties. You know, the taxpayers who paid for that grant money. They want to be able to get value out of that data. And so you need to make it available, which means if it's useless, if it can't be read on any other kind of machine, then you're probably not meeting the requirements of the data management plan that you were required to file with the grant proposal. And over time, it may be that the standard format changes, in which case you're doubly screwed. Okay. So it turns out there are a number of portable binary formats, and we're only going to look at one of them in detail. It's not even that much detail, but there are a number of them. I confess a certain amount of bias in favor of HDF simply because I did my dissertation at NCSA, and so I know those folks, and we hung out a little bit and that sort of thing. So the unit data people are also very nice people. So I don't have a bias against them. It's just I have more experience with HDF. So I'll talk a little bit more about that. So the advantage of portable I/O. So you've got the portable binary, which is what you want. You want to be able to read the data on any kind of machine for many, many years to come, arguably forever. They're typically relatively straightforward to use. I never want to use the word easy in a context like this. You have to take a little time to learn, but usually there are enough people around you in your research community to help you learn. It's not that bad. And the documentation, I mean, they've had years to refine it and make it reasonably readable. Most of these are available for free, so you just download them and install them. They typically run on most kinds of computers. And what's wonderful is they let you put metadata, data that describes your data, into the file where the data is, so that the file describes itself. And even if it has a non-helpful file name like X, you can still find out what's in it. Right? By the way, do not name your files X, just for the record. Give them meaningful names. Should mean things. That's a good rule of thumb. And you can put all kinds of interesting information about your data into the file. And typically they have sort of standard things you can put in, but then also the ability to just create new things that nobody has thought of previously. Okay. And on top of that, both HDF and NetCDF allow you to do parallel I/O, so you can have all of your processes writing to either different files or the same file all at the same time. And that works great on a parallel file system. Okay. All right, so, wow, all right, how are we doing on time?
It is 1:12.
All right, I probably will give people a few minutes of their life back. So if we think back to the very first lecture when we did the jigsaw puzzle, before we did the jigsaw puzzle, we talked about what do people use supercomputing for, and we said 3 things. This is not an exhaustive list, but it's sort of the most popular: simulation, data mining, and visualization. And visualization means turning data into pictures. And the reason that we want to turn data into pictures is because data are hard for human beings to understand, especially at the quantities of data, the amounts of data that we're dealing with nowadays, let alone where we're headed in the future, right? So nowadays, it's normal to have a terabyte of disk, in fact, multiple terabytes of disk on your laptop. This is not everybody has that. In fact, my laptop has a bit under a terabyte, but it's not at all unusual for someone to have a terabyte hard drive on their laptop. We think of a terabyte as a normal amount of data, but what that tells us is we're not too many years away from thinking of a petabyte as a normal amount of data. So terabyte, that's 1 trillion bytes. A petabyte, that's 1 quadrillion bytes. We're not that many years away from 1 quadrillion bytes, maybe not on your laptop. Well, I don't know. You know, maybe by the day I die, I'll have a petabyte on my, well, the day before I die. The day I die, it's not that useful. But the day before I die, maybe I'll have a petabyte of disk on my laptop, right? So, and trying to look at just the big pile of numbers is not going to help. So we need a way to turn our numbers into something that's intuitive and straightforward for us to understand. So turning the data into pictures or movies or even a video game, something you can interact with, is really great. Some kind of nice virtual reality thing that you can walk around in. Now, this was actually from my dissertation, believe it or not. This is right out of the dissertation document. I got this from a colleague. It was a simulation of Comet Shoemaker-Levy 9. This was a comet that hit Jupiter in the mid-90s. And this is the moment that it's passing from the sort of sparse, the sort of light outer atmosphere to the dense inner atmosphere. And you can see what it's actually doing is it's blowing up. It's exploding, right? The comet is blowing up as it gets into the dense inner atmosphere. And so this was, I ran this through the particular thing I was creating using my colleagues' data and simulation, and it did beautifully. It was wonderful. And so this is the comet blowing up. But if I just handed, his name is Mordecai Mark McLow. If I just handed Mordecai Mark a pile of data, it wouldn't really have helped him understand. By turning it into a picture, we can understand what's going on, right? Okay. So there are a number of ways that we can look at the data, and these are just some examples, right? There's a zillion other ways, and different kinds of data have different ways of looking at them. So if you're going to look at, for example, bioscience data, it's going to have a different way of visualizing than this. If you're going to look at social science data, there's different ways of visualizing that. Lots of different ways to visualize data. This is just one set of examples for physical data. Okay. So we start with, and I know these are a little hard to see from a distance. We start with contour lines. So we put a plane through the volume that we're looking at. And then on that plane, these different lines represent where we transition from one set of values to another. And I can't really see what's here, but here is relative humidity. So this is some weather data, right? And here's a plane that slices through a 3D box. And on that plane are the different humidity values. So, over here might be like 80% humidity, and then this is like 60% or whatever. I'm making the numbers up, but that sort of gives you the flavor of it. Now, a slice plane, same kind of idea, but now you can color code it. And so you can actually get multiple different variables onto this thing. So here I've got, I'm passing this through the box, and it's just a single plane. And by the way, typically, you don't have to have the plane be parallel to the axes. You can have it tilt in whatever direction you want. Okay. And then this one is colored by vorticity, so swirliness. And you can see it's very swirly here, and it's not terribly swirly here. Okay. All right, an isosurface. So this is like a contour diagram, except it's in 3D. So I picked a value. So the shape of this surface is where temperature is 0 degrees Celsius. But then I colored that shape, where temperature is 0 degrees Celsius. I colored it with the pressure. So the blue area is an area of low pressure. The green area is an area of medium pressure. If it were high pressure, it would show as red. Okay. And that's a fairly typical coloring scheme, although by no means the only one. Okay. Streamlines, now the idea is to start trying to capture movement, not just what it is at the moment, but how things are moving around. So now what we're trying to do is show where the velocity is going, right? To give a sense of how things are moving around. So here would be some kind of vortex where things are kind of going in a circle around it, for example. And then this one is fun. I stole this from one of my office mates in grad school. He's been very nice about that. So a volume rendering, thinking of that box as being filled with colorful smoke, where the smoke represents one quantity, how thick the smoke is, the opacity of it represents one quantity, and the color represents another. So in this case, the thickness of the smoke is the density, and the color of the smoke is the energy. So we can actually see two quantities very clearly, and this was a simulation of the early universe, where it's starting to break into, you can see filaments, and then these red bits are superclusters of galaxies. This is a cosmology simulation. These guys study the entire universe over its entire lifetime, right? So this was, I don't remember what time of the universe it was. Maybe this was now, I can't remember. And actually what we found from looking at this picture was our simulation was wrong, because it turns out the universe doesn't look quite like this. So we had to run a new simulation. And by we, I mean them, because I was just providing the capability. But turning this whole thing into this beautiful picture that looks like colored smoke to help us understand what was happening in the universe at that time. Okay, and that's it. I ended late, or early rather. I can give you a few minutes of your life back. And do we have anything from TV Land? Okay, thank you everybody. And we'll do this again in 2 or 3 years. But in the meantime, the videos are available on YouTube. So you're welcome to use all of those. And thank you everyone for being here with us. We've had a wonderful time together. And come to all the wonderful events.